Dear Chairman, dear colleagues, welcome everyone. I'm Tibor Tajti from the Esterházy Károly College, and I will talk about our indoor localization research and experiments using mobile phone. First, on the previous slide, it can be seen that it is sponsored project, and in this project, our research group is dealing with hybrid technologies using RFID and NFC technology combined with other technologies. We are focusing on possibilities built on sensory data, looking for application areas where we can use these hybrid technologies. One focus is the localization, and our hybrid devices are the mobile phones, these new smartphones. The indoor localization is one important focus for us because we see that there is a huge demand for it, and not yet solved. It could be used well in universities, institutes, shopping centers, deep garages. Probably it happens sometimes with everyone that we cannot find very easily our car in the deep garage. There is an alliance for indoor localization technologies called In-Location Alliance. Indoors, the GPS is not available, so we have to look for other possibilities, which are the RSSI information. In the previous talk, we have heard about it. We can use reference points using NFC tags, QR codes where the NFC is not yet available, and possibly user input or other reference point informations. The map can be used to know about walls, which also can give us information at least where we cannot be. This is also information. And we can have lots of information about moving from the sensors in the mobile phones. The mobile phones have lots of capabilities. What we need, the display, the camera, the computing performance of it. We could use RFID as well via USB or Bluetooth interface, but we are focusing on NFC and the sensory data. We have lots of sensors, not in every mobile phone, but most mobile phones have at least a few sensors from this list: the accelerometer, the magnetic field sensor, the gyroscope, gravity sensor, which is a computed information from the accelerometer. The linear acceleration is also a computed, not real sensor. We can have the rotation vector for example, the Android operating system. We have lots of libraries which can supply us sensor fusion, so we can get the rotation vector. Yes, in other name, the orientation. and at the end of the list occurring the step counter, which is also available in the newest phone sometimes. We are focusing on the Android, gathering the sensory data. We developed the NFC communication and QR code generation and reading for the reference point informations, and we are uploading this, the gathered data to a database where we can run the test and the analyzation algorithms in Python framework, trying to apply noise filtering. We are also trying to combine several different algorithms to get the best result, and we are also doing neural network experiments to see whether it works or not. Here's the data model. We are also presenting metadata for the measurements. It is not very important, and then we can query the database and see who did which experiments, short description of the experiments, and then we then can understand better what we see on the diagrams. For example, one important sensor is the magnetometer, which can give us absolute orientation, but unfortunately it is not very reliable because lots of problems can disturb the results. This measurement was made in a steady position, so the mobile phone was left on the desk, and only a second mobile phone was put into near and far, and these changes was made by these other device. So we cannot rely only on the magnetometer. The accelerometer also has problems, at least noise, very much noise, and also we can see that the vertical sensor gives a calibration error, so we also have to do a calibration. Okay, so this experiment was made some forward and backward moves of the mobile phone. It seems quite okay, but when we summarize the data to get the position, so the distance from the original position, then we see that this movement was done only in 1 meter, and the two opposite directions have 2.5 meter distance, which is not correct. Okay, so what we can do to deal with the noise and the other errors, we can use step counting. I will have a few slides about it, using reference points and noise filtering or neural networks, which we can try to teach to give better results from the data we have. So this step counting also has some errors. This small example was just I made work in a square, and it seems that the final position is not where it should be. The reference points we have used is were in QR code and on NFC tags. These are just examples of the QR codes having coordinates. I have not made a photo of the NFC tag. This is one work in a room. It is quite okay with little errors. I just made two screenshots. This map was displayed on the mobile phone, and the route was signed on the map. Okay, so again, some diagrams. If I made a few minutes of walking, just roundabout and roundabout, the cumulated error is the from the acceleration we get the velocity, and from that we compute the position. I started here, just a 3 meters circle, and at the end, the computed result gives more than 1,000 meters away from the starting point. So this is a very huge error, but when I use the reference point information, here was a reference point, then of course this error can be made smaller. In the next step, we have tried to transform the points between the two reference points, because here is a jump when I correct the position to the reference point, what I have read from the QR code or from the NFC, and this is smooth via transformation. Okay, this is again a diagram about the acceleration data. We can see the when we walk, then in all three coordinates, there is movement, which we can use for step counting as well. Then we have combined these two methods, three methods. One is to have the computation made from the acceleration data. This is the yellow lines. These are corrected with reference points. The red line is using the step counting method, and then we have made an average of these two methods, and it seems that it is better. So we can use these several methods to combine them and have better results. In the plans, we have also combining yet more methods. We are already trying to use neural networks, but we have not finished with yet. Also checking more noise reduction algorithms, for example, Kalman filter and other algorithms. And we are already collecting RSSI information, but we are not yet using these trilateration and triangular methods to get one more data for the position. And the next will be to try to keep the point on the way when we have a map about the area where we are. And thank you for the attention.